Today I am Minakshi, student of BSc Chemistry Honors, second year, 4th sem from Pandit Nikiram Sharma Government College, Rohtak. Today I am going to read the chapter Nitro Compounds. Here we start with the introduction. Nitro compounds constitute an important class of organic compounds. These may be considered to have been derived from the corresponding hydrocarbons by the replacement of one or more hydrogen atoms or by the nitro group. They are further classified as aliphatic or aromatic nitro compounds according as the nitrogen group is attached to alkyl or aryl group. RNO2 here R is a alkyl group is a aliphatic nitro compound, and ARNO2 where AR is a aromatic group aryl group. So ARNO2 is a aromatic nitro compound. Nitroalkenes are further classified as primary, secondary and tertiary according as the nitro group is attached to a primary, secondary or a tertiary carbon atom. Thus, primary nitroalkene, secondary nitroalkene and tertiary nitroalkene having the structure respectively RCH2NO2, R2CHNO2, R3CNO2. Since the nitro group is isomeric with the nitrite group, nitro compounds are isomeric with the alkyl or aryl nitrites. The chemical properties of these two isomeric classes of organic compounds are quite different, but the nitro compounds are much more stable and find number of applications both in the laboratory as well as in the industry. Therefore, in this unit we shall briefly discuss the study of chemistry of nitro compounds only. Structure of nitro group. According to the valence theory, the structure of nitroalkanes may be written as R N double bond O and single bond O. Single bond is here not a completely covalent bond. RNO2 double bond O, single bond O, or compound is polar because oxygen has more electronegativity than the nitrogen. So we can say nitrogen has slightly positive charge and oxygen has slightly negative charge due to the electronegativity difference. The polar structure of the nitroalkanes is supported by the large dipole moment. Thus, the nitroalkanes may be represented as the resonance hybrid of following two canonical structures: canonical structure 1 and canonical structure 2. The resonance hybrid structure 3 suggests that the two NO bonds are equal. The spectroscopic and diffraction studies have shown that the bond length of NO bonds is 121 picometer in nitromethane, which lies in between NO single bond length of 136 picometer and NO double bond of bond length 114 picometer. Nomenclature. Nitro compounds are solely named by the IUPAC system. The name of any nitro compound is derived by adding the prefix nitro to the name of corresponding alkene or the arene. Accordingly, aliphatic nitro compounds are called nitroalkenes, while aromatic nitro compounds are called nitroarenes. The position of the nitro group and the other substituents, if any, on the present parent nitroalkene or the nitroarene are indicated by the Arabic numbers 1, 2 and 3, etc., with the carbon atom bearing the nitro group getting the lowest possible number. For aromatic nitro compounds, prefix ortho for 1 2, meta for 1 3 and para for 1 4 are used. Some typical examples are given here below, such as nitromethane, nitroethane, 1 nitropropane, 2 nitropropane, 2 methyl, 1 nitropropane, 2 methyl, 2 nitropropane, 2 nitroethanol, 2 methyl 1, 4 dinitrobutene, 3 bromo, 3, 5 dimethyl 1, 5 nitroheptane, or the aromatic compounds where we say nitrobenzene, 2 nitrotoluene, or we can say orthonitrotoluene, 4 nitrotoluene or paranitrotoluene, 1, 3 dinitrobenzene or meta-dinitrobenzene. Preparation of nitro compounds. The preparation of nitroalkenes. From alkenes. Alkenes undergo nitration only with fuming HNO3 in the vapor phase at 673 Kelvin to form nitroalkenes. This method is called vapor phase nitration. Here methane reacts with fuming HNO3 at 673 Kelvin gives nitromethane plus water. Nitromethane here formed is in low in yield. Limitation. Nitration of higher alkenes not only gives a mixture of all the isomeric nitroalkanes but other nitroalkanes containing lesser number of carbon atoms resulting through the cleavage of carbon-carbon bond are also formed. Besides these, oxidation products like CO2, NO2, H2O, etc. are also formed. Nitroethane here reacts with fuming HNO3 gives nitroethane plus nitromethane. Here nitromethane is formed 20%. Propane reacts with fuming HNO3 gives 1 nitropropane 25% yield and 2 nitropropane 40% yield. Nitroethane 10% yield and nitromethane 20% plus other oxidation products are also formed. The reaction occurs by the free radical mechanism and the ease of the substitution of hydrogens follows the order tertiary, secondary and primary. Merits. Due to the formation of complex mixture of product, this method is not suitable for laboratory preparation of nitroalkenes. However, this method is widely used for commercial preparation of nitroalkenes. From alkyl halides, alkyl bromides and iodides, especially primary and secondary, reacts with the silver nitride in alcohol to give excellent yield 70 to 80% of nitroalkane along with small amounts of alkyl nitrides. Alkyl halides here reacts with silver nitride in the presence of alcohol and heat gives nitroalkane, that is a major product, and alkyl nitride, that is minor product. Example I am giving here is 1-bromobutane reacting with silver nitride in presence of alcohol and heat giving 1-nitrobutane 75% and N-butyl nitride 13%. Here AgBr is formed in the product sites. Explanation. This reaction is example of nucleophilic substitution reaction. Nitrite ion, like cyanide ion, is an ambident nucleophile since it has two sites, oxygen and nitrogen, through which it can attack an alkyl halide. Whereas attack through nitrogen gives nitro compound, attack through oxygen gives nitrite. Here AgNO2 in silver nitride reacts with alkyl iodide gives nitroalkane plus AgI, मतलब silver iodide. This AgNO2 here in this reaction is in covalent form, or we can say the bonds here are covalent bonds. In the next reaction, sodium nitrite reacts with alkyl iodide. Here the bonds are ionic. It reacts to form alkyl nitrite and NaI, sodium iodide. Alkali metal nitrides are ionic compounds and hence have a negative charge on the one of the oxygen atoms. Nucleophilic attack through this negative charge oxygen atom on the alkyl halides mainly gives alkyl nitrides. In contrast, silver nitride is a covalent compound and hence does not have any negative charge on the oxygen atom. Instead, both oxygen and nitrogen atoms carry lone pair of electrons. Since the nitrogen is less electronegative than the oxygen, therefore lone pair of electrons on the nitrogen are more easily available for bond formation. In other words, nucleophilic attack occurs through nitrogen and hence silver nitride predominantly gives nitro compounds. Demerits. Aromatic nitro compounds cannot be prepared by this method. This method is not suitable for the large-scale preparation of nitro compounds. For tertiary alkyl amines, primary amines containing tertiary alkyl group on oxidation with KMnO4 give excellent yields of corresponding nitroalkanes. For example, 2-methylpropane 2-amine, or we can say tert-butylamine reacts with KMnO4 gives 2-methyl 2-nitropropane in 83% yield. Preparation of nitroarenes. Nitroalkanes are invariably prepared by direct nitration of arenes with mixture of concentrated HNO3 or fuming HNO3 or concentrated H2SO4. For example, benzene reacts with HNO3 concentrated H2SO4 in 3333 Kelvin gives nitrobenzene plus water. The mixture of concentrated HNO3 and concentrated H2SO4 used for nitration of aromatic compounds is called the nitrating mixture or the nitrating agent. Other nitrating agents which have been used for the nitration of aromatic compounds are called nitric acid, acetic anhydride mixture, acetyl nitrate, nitronium perchlorate, nitronium tetrafluoroborate, Mechanism. Nitration is a typical example of aromatic electrophilic substitution reaction in which the nitronium ion acts as an electrophile. The function of H2SO4 is not that of dehydrating agent but acts on HNO3 to form a reactive nitronium ion as shown below. Here nitric acid reacts with H2SO4 gives nitronium ions plus H3O positive plus 2HSO4 negative. This electrophilic substitution reaction occurs by the following two-step mechanism. First step, benzene and other arenes are electron-rich molecules. In the first step, the electron-rich benzene molecule nucleophile attacks nitronium ion electrophile leading to the formation of a carbocation 1 which is stabilized by the resonance. During this step, the aromatic character resonance energy of 150 kJ per mole is sacrificed. As a result, this step is slow and hence is called the rate determining step of the reaction. In the second step, the carbocation 1 formed in the step 1 loses a proton to yield nitrobenzene. Since during this step the aromatic character of the benzene ring is restored, this step is fast and hence does not affect the rate of the reaction. Evidence in the support of the mechanism. This mechanism is supported by the isotope effect. It has been found that when hexadeuterobenzene is nitrated, the rate of nitration is exactly the same as that of benzene. Since CD bond breaks more slowly than CH bonds, therefore the loss of proton is not the rate determining step. Had it been so, the rate of nitration of benzene and hexadeuterobenzene would have been difficult. Benzene on nitration gives nitrobenzene. Hexadeuterobenzene on nitration with HNO3 and H2SO4 gives 2, 3, 4, 5, 6 pentadeuteronitrobenzene. The choice of nitrating agents. The choice of nitrating agents to be used for nitration of a given compound depends on the following two factors. Nature of the compound to be nitrated, number of nitro groups to be introduced. The presence of electron donating substituents like CH3, OCH3, OH, NH2, etc. activates the benzene ring by stabilizing the intermediate carbocation. Therefore, nitration of these compounds is carried out under mild conditions. For example, nitration of phenol occurs with dilute HNO3 even at room temperature. Here phenol reacts with dilute HNO3 gives orthonitrophenol and paranitrophenol. Orthonitrophenol is a major product here. In contrast, the presence of electron withdrawing groups such as NO2, COH, CN, SO3H, halogens deactivate the ring by destabilizing the carbocation. Therefore, the nitrating such compounds, or when if is required to introduce more than one nitro group, the nitration is carried out not only by using a strong nitrating mixture but a higher temperature is also required. For example, nitration of nitrobenzene, which contains the electron withdrawing NO2 group, is carried out with a mixture of concentrated HNO3 plus concentrated H2SO4 at 393 Kelvin. The physical property of nitro compounds. The physical state, color, odor, etc. The nitroalkanes are colorless when pure, pleasant smelling liquids. Aromatic nitro compounds can be either pale yellow liquids or solid with distinct smells. For example, nitrobenzene is a pale yellow liquid having the smell of bitter almonds is known as oil of myrrhine. Boiling points. Both nitroalkanes and nitroarenes are highly polar compounds. Dipole moment between 3 to 4 D and thus have strong dipole-dipole interaction. As the result, they have much higher boiling points than the hydrocarbons of comparable molecular masses. For example, further nitroalkanes also have much higher boiling points than the less polar isomeric alkyl nitrites. For example, boiling point of ethyl nitrite is 261 Kelvin while the isomeric nitroethane has a boiling point of 388 Kelvin. Density. All the nitroalkanes and nitroarenes are heavier than water. Solubility. Nitroalkanes are sparingly soluble in water while nitroarenes are insoluble. However, both the nitroalkanes and arenes are readily soluble in organic solvents. Stability. When heated strongly, polynitro compounds decompose with explosive violence. Chemical reaction of nitroalkanes. Tautomerism. Like aldehyde and ketone, nitroalkanes containing alpha hydrogen atoms that is primary and secondary nitroalkanes show tautomerism. For example, nitromethane exists in two tautomeric form, nitromethane, nitrofem or pseudoacid form. In other form, acinitroform or isonitroform or nitronic acid form. The nitroform 1 is called pseudoacid form while the isonitroform second is the acinitro or nitronic acid. The equilibrium, however, almost completely lies toward left due to the resonance within the nitro group. Stabilization of nitroform 1. Similarly, the nitroethane 1, nitropropane 2, nitropropane show tautomerism, while aromatic nitric compounds nitrobenzene, metadinitrobenzene, etc., which do not contain alpha hydrogen, do not show tautomerism. Acidic character. The alpha hydrogen atoms of the primary and secondary nitroalkanes are weakly acidic and thus can be abstracted by strong alkalis such as NaOH. Therefore, primary and secondary nitroalkanes dissolve in aqueous NaOH to form salts. For example, NaOH reacts with nitroalkane, gives R CH negative, single bond N positive, double bond O negative. The main reason of the acidic nature of primary and secondary nitroalkanes are the strong electron withdrawing inductive effect of the nitro group and the second, the resonance stabilization of the carbon ion formed after removal of a proton. Although primary and secondary nitroalkanes are weakly acidic, yet as compared to aldehydes and ketones, they are twice as strong. For example, pKa of nitromethane is 10.2 while that of acetone is 20. Nevertheless, nitroalkanes are neutral to litmus. Acidification of a sodium salt 1 within the weak acid gives the nitro analog of an enol called the acinitrotautomer. Unlike the enols of aldehyde and ketone, which are readily converted into the keto form, the conversion of acinitroform into nitroform is a relatively slow process. Consequently, acinitroform can be generated as a metastable intermediate in the high concentration by careful acidification of the salt. Acinitro derivatives are relatively stronger acids as in the evident form their pKa value. Reactions of acinitroform with electrophiles and nucleophiles. One of the remarkable feature of acinitroforms is that they can behave as nucleophile as well as electrophile and thus react with electrophilic and nucleophilic reagents. Reaction in which acinitro derivative act as a nucleophile. Some of these type of reaction are discussed here. Aldol condensation, the carbon ion of the nitroalkanes being nucleophilic reacts with electrophiles such as aldehyde and ketone to form aldol type addition product which spontaneously undergo dehydration to give alpha beta unsaturated nitro compounds. For example, here the reaction is given. Driving force of this dehydration is the gain in stability due to the conjugation of ethylene double bond with double bond of the nitro group. Michael addition. Like aldehyde and ketone, alpha beta unsaturated carbonyl compounds act as electrophile and thus reacts with nucleophilic acinitro to form Michael type addition product. For example, nitroalkane reacts with OH slow step gives acinitroform, that is act as a nucleophile, then undergo Michael addition to form addition product. Halogenation. Acinitroforms being nucleophile react with electrophiles such as halogens in the presence of alkali to form halonitroalkanes. During this reaction, all the alpha hydrogen atoms of the nitroalkanes are successively replaced by halogen atoms. Tertiary nitroalkanes do not undergo halogenation because they do not have alpha hydrogen atoms. Chloropicrine obtained above is used as an insecticide as well as a constituent of tear gas. The reaction in which acinitroform act as an electrophile. An important reaction of this type is Neff-carbonyl synthesis. Neff-carbonyl synthesis, when the solution of sodium salt of nitronic acid is acidified with H2SO4 at room temperature, 1 degree nitroalkanes give aldehyde while 2 degree nitroalkane gives ketone. During this reaction, the acetonitrofoam act as electrophile and water act as a nucleophile. For example, sodium salt of nitronic acid reacts with H2SO4 gives electrophile. Electrophile then interacts with nucleophile gives a product that is aldehyde finally. Similarly, sodium salt of nitronic acid derived by secondary nitroalkanes on treatment with 50% H2SO4 gives ketone. This reaction is called Neff carbonyl synthesis. The main disadvantage of Neff carbonyl synthesis is that reaction is often violent and gives unsatisfactory yield. Hydrolysis. The primary nitroalkanes, when treated with boiling HCl or 85% H2SO4, undergo hydrolysis to form carboxylic acid and the corresponding salt of hydroxylamine. Nitroalkane reacts with HCl plus H2O gives RCOO NHOH reacts with HCl plus H2O gives carboxylic acid and hydroxylamine hydrochloride. This reaction is used for the manufacture of hydroxylamine. In contrast, secondary nitroalkanes upon hydrolysis with boiling HCl gives ketone and nitrous oxides. The tertiary nitroalkane, however, do not generally undergo hydrolysis with hydrochloric acid. The action of nitrous acid. Primary, secondary and tertiary nitroalkanes behave differently towards nitrous acid. Primary nitroalkane react with nitrous acid to form nitrolic acid which dissolve in alkalis to form red solution. Secondary nitroalkanes react with nitrous acid to form blue-colored pseudo-nitros which do not dissolve in alkali. Tertiary nitroalkane do not react with nitrous acid since they do not have alpha hydrogen atoms. Mannich reduction. Primary and secondary nitroalkanes undergo Mannich reduction. For example, primary nitroalkane reacts with dimethylamine. It gives RCHNO2 CH2 NHCH3 twice plus H2. This reaction can be used for the preparation of nitroamines and diamines. Reduction. One of the most important reactions of nitro compounds is their reduction. Depending upon the nature of the reducing agent, the pH of the reaction medium, the nitroalkanes give different product as shown below. Reduction in acidic medium, nitroalkanes can be reduced to the corresponding primary amines by the combination of some active metal like zinc, iron, or tin and concentrated hydrochloric acid. For example, nitroethane reacts with SnHCl gives ethylamine. Hydrochloric acid reacts with NaOH gives ethylamine plus salts. The reduction in the neutral medium. In the neutral medium, zinc dust in NH4Cl solution, nitroalkanes are reduced to corresponding hydroxylamines. For example, nitromethane reacts with 4H nascent hydrogens in presence of ZnNH4Cl plus H2 gives N-methyl hydroxylamine plus water. Catalytic reduction or reduction with lithium aluminium hydride. Nitroalkanes can also be reduced to the corresponding primary amines with either lithium aluminum hydride or with H2 in presence of catalysts such as Ra, nickel, platinum, palladium, carbon, and ethanol. Some chemical reaction of nitroarenes. Acidic nature. Unlike primary secondary nitroalkanes, nitroarenes do not give any alpha hydrogens. Therefore, like tertiary nitroalkanes, they do not exhibit acidic character or tautomerism. However, nitro compounds having two or more nitro group attached to the benzene are somewhat acidic. Thus, polynitro compounds often react with cold aqueous alkali to form strongly colored salts. Reduction. One of the most important reactions of nitro compound is their reduction to primary amines. This reduction is believed to occur through the following steps. Here the nitro compounds gives water, form nitroso compound, then a substituted hydroxylamine, then it again form primary amine. The final product, however, depend upon the pH of the reaction medium and the nature of the reducing agent. Reduction in the acidic medium like aliphatic nitro compounds, aromatic nitro compounds can We reduce two corresponding amines by combination of some active metals like zinc, iron, and tin. Concentrated hydrochloric acid, for example, nitrobenzene reacts with FeHCl, gives aniline hydrochloride, then it again reacts with NaOH, gives aniline. Under acidic condition, the intermediate product are reduced even more readily than the parent nitroatom, and hence only the primary amine is obtained as the final product. Mechanism. The mechanism of the reduction of nitro compounds to amine involve a number of steps in which the addition of electrons and protons from the acids takes place in nitrobenzene and phenyl hydroxylamine are the intermediates. These hydroxylamine, when warmed with Tollens reagent, are easily oxidized back to the corresponding nitroso compounds and thus reduce Tollens reagent to metallic silver. This reaction is used as a test for nitro compounds under the name Baker's-Milkans test. The reduction in the alkaline medium. The reduction of the aromatic nitro compounds in the alkaline medium gives different bimolecular reduction products depending upon the nature of the reducing agent employed. For example, nitrobenzene here reacts gives three different products with three different reagents, that is azobenzene, hydroxybenzene, and azoxybenzene. These bimolecular reduction products are actually formed by the condensation of primary products of the reduction, nitrosobenzene and phenylhydroxylamine. Azoxybenzene is formed by the base-induced condensation of nitrosobenzene and phenylhydroxylamine. Similarly, it can be shown that further reduction of azoxybenzene first gives azobenzene and then hydroxybenzene. Reduction with lithium aluminum hydride. Reduction of nitrobenzene with lithium aluminum hydride also yields azobenzene. It may be noted here that the reduction of aliphatic into aromatic compounds with lithium aluminum hydride, however, gives the corresponding primary amines. The electrolytic reduction of nitrobenzene in weakly acidic medium gives aniline, but strongly acidic medium it gives para aminophenol, obviously through the acid catalyzed rearrangement of initially formed phenylhydroxylamine. Here nitrobenzene undergo electrolytic reduction in weakly acidic medium forms aniline, and nitrobenzene in the next reaction reacts with electrolytic in the electrolytic reduction under strongly acidic medium forms N-phenyl hydroxylamine, and then after going rearrangement it forms para-aminophenol. Selective reduction. If two or more nitro groups are present in the benzene ring, it is possible to reduce one of them without affecting the others. Such reductions are called selective reductions. For example, reduction of meta-dinitrobenzene with sodium and ammonium sulfide gives meta-nitroaniline. Meta-dinitrobenzene reacts with 3NH4 twice S gives meta-nitroaniline. This reduction of nitro compound with sulfides and polysulfide is called xenene reduction. Electrophilic substitution reaction. Nitro compounds, like other aromatic compounds, undergo electrophilic substitution reactions such as halogenation, nitration, and sulfonation. Since NO2 group is a powerful electron withdrawing group, it strongly deactivates a meta and it is strongly deactivating and meta-directing. This may be explained as follows. Nitrobenzene can be represented as a resonance hybrid of following structure. It is evident that nitro group, because of the electron withdrawing nature, reduces electron density more at ortho and para position than at the meta position. In other words, electron density is comparatively more at meta position than at ortho and para position. Therefore, nitro is a meta directing group. Further, since the NO2 group is strongly deactivating, therefore these reactions occurs at only under drastic conditions. For example, nitrobenzene reacts with fuming HNO3 plus concentrated H2SO4 gives meta-dinitrobenzene. Here nitrobenzene reacts with bromine and Fe gives meta-bromonitrobenzene, and then it reacts with fuming H2SO4. It forms meta-nitrobenzene sulfonic acid. It may be noted here that because of strong electron withdrawing nature of the nitro groups, the electron density on the benzene ring decreases to such an extent that meta-dinitrobenzene does not undergo further nitration to give a symmetrical trinitrobenzene. Therefore, it is prepared by indirect route. Nitrobenzene does not undergo Friedel-Crafts reaction. This is because of the reason that in many Friedel-Crafts reactions, nitrobenzene is used as a solvent. Another advantage of using nitrobenzene as a solvent in Friedel-Crafts reaction is that because of highly polar nature, it dissolves anhydrous aluminum chloride. Nucleophilic substitution reactions. The presence of positive charge at ortho-para position in the resonance structure 2 and 4 suggested that the nitrobenzene can also undergo nucleophilic substitution reactions at these positions. These reactions, however, occur with strong nucleophile under drastic conditions. For example, nitrobenzene, when fused with solid KOH, gives low yield of mixture of ortho and para-nitrophenols. Mechanism. The mechanism of this reaction is an example of bimolecular nucleophilic substitution reaction. In the first step, nucleophile adds to the benzene ring to form a carbon ion, which is stabilized by resonance, also involving the nitro group. In the second step, the carbon ion 1 loses a hybrid ion, which is very strong base and hence a poor leaving group. Therefore, the reaction is usually carried out either in high temperature or in the presence of an oxidizing agent which oxidizes H negative ion to H2. The complete mechanism is outlined below by the consideration of formation of para-nitrophenol. Replacement of nitro group. We have seen above the nitro group of the nitrobenzene remains intact on the treatment with alkali. However, this nitro group can be displaced as nitrite ion by nucleophiles if another nitro product is present at ortho or para positions. Here, orthodinitrobenzene reacts with aqueous KOH, gives orthonitrophenol plus KNO2. Then again further, orthodinitrobenzene reacts with alcoholic KOH, gives orthonitrophenol, orthonitrophenitiol. And again it reacts with 2NH3, gives orthonitroaniline. Orthonitroaniline plus N2 plus 2H2. Picric acid 2,4,6 trinitrophenol. Direct nitration of phenol with mixture of concentrated HNO3 plus concentrated H2SO4 gives only a low yield of picric acid because nitric acid, being a strong oxidizing agent, oxidizes phenol to terry products. It is therefore prepared commercially by the following methods from phenol. Phenol is first sulfonated to give phenol 2,4-disulfonic acid, which is then nitrated. During nitration, the two sulfonic acid groups are replaced by nitro groups and the third nitro group is introduced to the ortho position. Phenol here reacts with concentrated H2SO4, gives phenol 2,4-disulfonic acid, then it again reacts with concentrated HNO3 plus concentrated H2SO4 and forms picric acid, as I have told you the formula of picric acid above. From the chlorobenzene, picric acid is obtained from the chlorobenzene by the following sequence of reaction. Chlorobenzene on nitration in the presence of concentrated HNO3 plus H2SO4 gives 2,4-dinitrochlorobenzene. Further, on the nucleophilic substitution reaction in the presence of aqueous Na2CO3 gives 2,4-dinitrophenol, and further it reacts with HNO3 and H2SO4 gives picric acid. Physical property: it is a yellow crystalline solid, melting point 395 Kelvin, sparingly soluble in water but readily soluble in alcohol and ether. It has a bitter taste and hence the name Greek picrus means bitter. Chemical properties. Some important chemical properties of picric acid are described below. Acidic nature: due to the presence of 3 nitro groups, picric acid is very strong acid pKa and hence decomposes carbonates and bicarbonates evolving CO2. Picric acid reacts with NaHCO3 gives a product where it gives bicarbonate. or carbonate plus CO2 plus H2. Reaction with PCl5. When treated with PCl5, it forms picryl chloride. The chlorine atom is picryl chloride, is very reactive and thus get hydrolyzed to phenol on boiling with water. On treatment with concentrated ammonia, picryl chloride gives picramides. Reduction. On selective reduction with Na2S, picric acid gives picramic acid. Picric acid reacts with Na2S, gives picramic acid. Formation of picrites. It forms charge transfer complex known as picrites with electron-rich compounds such as aromatic hydrocarbons, amines, and phenols. Picrites are yellow, orange, or red colored solid with definite melting definite melting points, and hence are often used as a derivative to characterize above classes of compounds. Uses. Picric acid is used as an explosive as in direct yellow dye for wool and silk, and in the medicine as an antiseptic for burn. It is also used as a laboratory reagent for characterization and purification of polynuclear aromatic hydrocarbons, amines, and phenols. Halonitroarenes. Arenes containing both halogen and nitro groups are called halonitroarenes. For example, there are three isomeric halonitroarenes having one halogen atom and one nitro group attached to the benzene ring. Chemical reactivity of halonitroarenes. Halonitroarenes are unreactive towards nucleophilic substitution reaction, but the presence of nitro groups at ortho and para position with respect to the halogen atom facilitates nucleophilic substitution reaction of halonitroarenes by stabilizing the intermediate carbon ion, as shown below. Evidently, more the number of nitro groups at ortho and para position with respect to halogen, more reactive it is. It may be, however, be noted that the presence of nitro group at meta position with respect to the halogen does not activate the halogen to the same extent as at ortho and para position, since the carbon ion is only stabilized by the weak minus I effect and does not by the strong minus R effect of the nitro group. Thank you for your patience. Thanks for listening the audio lecture.